Okay, on to question 91. Which circuit diagram shows the voltmeter and ammeter correctly positioned? Well, voltmeter is in parallel and ammeters are in series. And we want to measure the total potential difference of the circuit and the current through each resistor. So if we want the total potential, you need to do a voltage. I mean, this is in series, so that's not going to work. This is in series, so that's not going to work. This right here will get the voltage of both resistors, and that should be equal to the voltage of the battery. That is not going to get the current. Well, ammeter will get the current through each of those resistors. So I think that would be the correct one. This one right here, this voltmeter, is not going to let any current pass through there. So it, in theory, would measure the voltage of this, but it's not going to get the current. That would keep any current running through here. So this is getting the voltage of those two. You could also have a voltmeter placed here, which would get the same result. And the current through each resistor. Okay, and the current through each resistor is total current. Two resistors are connected to a source of voltage. Where should we put the ammeter to measure the current passing only through R1? So only through R1. We want an ammeter in series, so that means in position 3. That's pretty easy. The next 3 questions are based on this. What is the equivalent resistance of this circuit? So 1 over Req equals 1 over 20 ohms plus 1 over 30 ohms. 1 over 20 plus 1 over 30 is going to equal 3 plus 2 over 60. So that's 5 over 60. So that means Req, and I'll put an ohm in the bottom there, is going to equal 60, because the unit flips up top, 60 over 5 should equal 12 ohms. Answer B. What's the current reading of the ammeter? Okay, so let's think about it. Because this is a parallel circuit, both of these paths have a 12 volt difference. And through this ammeter here, you have a 20 ohm resistor that's resisting it. So if we look at this point right there, we can use Ohm's law. R equals V over I. And we know the resistance is 20 ohms. We know the voltage is 12 volts. We just need to find the current. I is going to equal 12 over 20. 12 over 20 should be 0.6 amps. What's the power of the 30 ohm resistor? Okay, so now we're going into power equations. Now there's multiple ways to do it. We want to look at the power of the 30 ohm resistor. Again, this 30 ohm resistor is 12 volts because both paths have 12 volts. So P, we know the resistance, we know the voltage, so we could just see P equals V squared over R. I mean, you can find the current and get that too, but let's just do 12 volts squared over 30 ohms. So 144. I'm sorry, 144 is 4.8 watts. Answer A. 1 watt. Well, if you're not sure about this, just look at the equation. Watt is a unit of power, right? Now, there's different ways to put it. So it could be a volt times an amp. It could be, and we'd have to actually look at this other section here. Power is equal to, let's see, the rate at which work is done. Is it here? So work is equal to power divided by time. So power is equal to work over time, which would be like a joule per second. So one of those is going to be there. Boom. A joule, by the way, is work is force times distance is a Newton meter. So it could also be a Newton times a meter per second, but not a Newton per meter. So there's work from the equations if you're not sure about that. While operating at 120 volts, a toaster has a resistance of 15 ohms. The power used by the toaster is. Okay, so again, we got to look and see what we know. We got the voltage, we've got the resistance. So power is going to equal V squared over R. 120 volts squared over 15 ohms. So this is assuming that, well, we don't need to know current. 120 squared divided by 15 is equal to 960 watts. There we go, answer C. As the potential difference across a resistor increases, the power expended in moving a charge through the resistor. Okay, so let's see, the power and potential difference against a given resistor. So that means R is constant. V changes. We want to find P. Because you can find P in terms of multiple variables, but let's find P in terms of R and V. So P is equal to V squared over R. Now if R is constant, we can ignore it and we just say P is proportional to V squared. So if the voltage increases, then the power should increase also, with the square of the voltage. So as the potential across a resistor increases, the power should also increase. Okay, the potential difference applied to a fixed resistance is doubled, so R is constant. Potential difference is V is doubled, so the power dissipated by that. So again, we need an equation that has P, V, and R in it, because R is constant, and we're going to let that go. So P is equal to V squared over R, so that means P is proportional to V squared. So if you double the potential difference, if you change that to like a 2V or whatever it is, you square it, you end up 4V squared, so it means it's 4 times bigger. If originally it was V squared, now it's 4V squared, so it should quadruple. Answer D. Identical resistors are connected across a 12-volt battery. Which circuit uses the biggest power? Okay. So 4 different circuits. Now, interestingly enough, we're going to know the voltage, and we're going to know the resistance. So again, we can use this equation, P equals V squared over R. And we can simplify these down into simple circuits. So we could say, okay, for this one, it's just 12 squared over R. Pretty straightforward, right? 12 squared is 144 over R. Now let's say we take this and we add another resistor. Well, you might think that the resistance is going up because you're adding another resistor, but in fact, resistance goes down. So you're going to get 144 over a smaller value of R. And if you get a smaller value of R, that means you're going to get a bigger power. So that means a bigger power. Because as R goes down, power goes up. As V goes up, power goes up. As R goes up, power goes down. As R goes down, power goes up. So the less resistance you have, the more power. And that makes sense, because less resistance is going to cause more current to flow. It's easier for current to flow, and that's going to lead to more power. So having said that, this one has more resistance. So more resistance is not going to get you more power. This one adds 2 more resistors, so this should have even less resistance, because the more resistors you add in series, the less overall resistance you have. So this one right here should have the lowest resistance and therefore the most power. Answer D. Just got to think through that a little bit. Okay, you get 2 resistors connected in parallel across a 6-volt source. Compared to the power dissipated in the 1 ohm resistor, the power dissipated in the 3 ohm resistor is, okay, so P equals, and again we know R and V. P equals V squared over R. I mean, you can even figure this out, because V is going to be 6 for both of them. It's a parallel circuit. So 6 squared is 36, divided by 1 ohm is 36 watts. This one right here, V squared over R, V is again going to be 6. 6 squared is 36. But now your R is 3. So you've got higher resistance. So now you have 12 watts. So this one has 3 times more, is 3 times more powerful than this one. So compared to the power dissipated by the 1 ohm resistor, the power dissipated by the 3 ohm resistor is less. 12 watts as opposed to 36 watts. The heating elements on an electric stove dissipate a bunch of power when they are connected to a 120 volt surface. What's the resistance? So in this, we're going to have power, voltage, and resistance. Well, there's a lot of PVIs. Okay. So if P equals V squared over R, R is going to be equal V squared over P. So V is 120 squared. P is 4 times 10 to the second, 400. So let's put this into the calculator. 120 squared divided by 400 gets us 36 ohms. Answer D. An immersion heater has a resistance and it draws a current. How much energy is delivered into the heater during a certain amount of time? So R is equal to 5 ohms. I is equal to 3 amps. We need to find work, because work is the same as energy. We know time is 200 seconds. So let's think about this. We need to find an equation for work. Work equals R, we know, I, we know, and T, we know. So I squared RT. I squared RT, which is going to equal 3 squared times 5 times 200 seconds. That's already in seconds. So 3 squared times 5 times 200 equals 9,000, which is 9 times 10 to the third. Answer C, joules. What's the total electrical energy used by a power for 6 minutes? Okay, that's in minutes, so it probably is going to need to be turned into seconds. We're looking for electrical energy given power, so work, which is energy, is equal power times time. Work is equal to power times time, which in this case is going to be 1,500 watts times a time of 6 minutes. But 6 minutes, and we turn minutes into seconds because 1 minute is equal to 60 seconds. So 6 times 60, dimensional analysis here, those minutes go away. 1,500 times 6 times 60, 540,000. So 5 times 10 to the fifth, answer D. An electric heater draws a current of 10 amps and has a resistance of 12 ohms. How much energy does the heater use in 60 seconds? So we have a current I of 10 amps, resistance of 12 ohms, and we need a time of 60 seconds. And we want to find the energy, so work. So we need to find a work thing that has I, R, and T, which is I, R, and T, the same equation that we're going to use, I squared RT. So I is going to be 10 amps, but that's squared. R is going to be 12. T is going to be 60. So let's do this. 10 squared times 12 times 60 should be 72,000. Answer D. For which quantities or values needed to calculate the amount of energy supplied by a toaster? So again, we're going to find energy. They're all giving us voltage, so that limits us a little bit. So it could be VIT, or it could be V squared T over R. Either one works because they both have voltage. So we need at least those. We need the time in both of them. So voltage and resistance, no, not going to do it. No time in there. Voltage and operational time, no, not going to do it because we need either R or I. Voltage, current, and resistance. No, we need a time. Voltage, current, and time. So answer D should be the right one. Okay. Gonna take a quick look to see how many more multiple choice questions we have. 2 pages. The total amount of energy delivered to the resistor in 10 seconds is, okay, so we have a resistor, it's got 4 volts, and we got a resistance, R equals 8 ohms, V equals 4, and T equals 10 seconds. Let's look at this. We want to find energy, that's work. We need to find R, V, and T. So V squared, T over R. So that is equal to 4 squared, that's 16, times 10, 160 divided by 8. So that should be probably 20, right? 4 squared times 10 divided by 8, 20 joules. Perfect. We have a cell that needs to be recharged. How much energy do you need? Okay, we've got a voltage is 1.5 volts. So in this case, we're looking at voltage is equal to W over Q. We're finding the energy, and we know the charge of an electron, E, is equal to 1.6 times 10 to negative 19th joules. So work is equal to VQ. When I said E, that's also Q, whatever you want to call it. E equals Q. It would be negative if it's an electron, but that shouldn't affect your results. 0.5 volts times 1.6 E negative 19 joules gets us 2.4 times 10 to the negative 19th. What did I not do? .4 times 10 to the 19th joules, right? Which isn't an answer, but let's try this in coulombs, or in electron volts, because we know that 1 joule is equal to, and I'm being stupid when I'm looking at this, because I didn't look at the answers first. Half these are in EV and half of them are in joules, so it should have been really easy. If 1 joule is going to equal 1.6 times 10 to negative 19th coulombs. No, sorry, I'm looking. 1 EV is equal to 1.10 to negative 19th joules. So I need to do this again. 1 EV, 1.6 times 10 to negative 19th joules. So if I divide that answer, we're going to see that it comes out to be 1.6 E negative 19. Let's delete that. Okay. 1.5 EV. So we just got an answer in EV. It's 1.5. It takes 1 electron volt to move 1 electron through a 1 volt potential difference. So if we're moving through 1.5 volts, it should take 1.5 EV. Pretty straightforward. I did more math than I really needed to. Okay. We're doing some field lines, north to south, right? So at which point is the magnetic field strength the greatest? It's when the lines are closest together, and they are closest together at point B, so that's going to be answer B. Okay. If they point north to south, let's think about it this way, and your compass will point in the same direction because your compass is a north-facing needle, so that means your compass will point that way, which should be answer B. So north to south, and your north-facing needle will point toward the south-facing magnet because it is attracted to it. Okay, a bar magnet, which arrow represents the needle. So north to south, boom, like this. So at that point right there, it should be pointing to the right. That's answer C. Which diagram represents the magnetic flux lines around a bar magnet? Okay, north to south. Well, they should not cross, so it can't be C or A because they both cross. And B, they point from south to north. And D, they point north to south, so it's got to be answer D. You're putting iron filings around a bar magnet, and this magnetic field is going to be strongest, again, where the lines are closest together. That should be point A. There we go. Let me stop here. We'll come back and start at 114 a little bit later, and we'll do the free response questions.